In this video, I will show you how to solve problems involving proportionality and differential equations. Write and solve the differential equation that models the verbal statement. Number 11, the rate of change of Q with respect to t is inversely proportional to the square of t. Quick side lesson. The statement y varies directly with x means that y is equal to k times x, where k is the constant of proportionality. On the other hand, if you see y varies inversely with x, it means y is equal to k divided by x. Back to number 11. The rate of change of q with respect to t just means dq dt. Is inversely proportional to means it's going to be k divided by whatever comes next. What comes next is the square of t, which is just t squared. This is a separable differential equation. So we want all of the q's on the left side of the equation, and we want all of the t's on the right-hand side of the equation. K is just a constant. The first step would be to multiply both sides of the equation by dt. That way, the dt will end up over here. This actually accomplishes my goal of having the q's on the left and the t's on the right. The only small change I will make is that instead of having t squared in the denominator, I'd rather write it as t to the negative 2 power. Solving a differential equation means getting this q by itself. I can accomplish that by taking the integral of both sides of the equation. The integral of dq is like the integral of 1 dq. The antiderivative is q. On the right-hand side, I'm going to just bring down my constant. I'm increasing the exponent by 1, so this will be t to the negative 1 power. And then I divide by the new exponent, which will just give me a negative in the front. Don't forget the constant of integration. This is a valid answer, but I think I would prefer to write it as q equals negative k over t plus c. This is the general solution to the differential equation because we don't have enough information to solve for c. We'll just leave it like this. Number 12, the rate of change of p with respect to t is proportional to 25 minus t. The rate of change of p with respect to t just means dp dt. And when they say is proportional to, it just means we're going to multiply k times whatever comes next. And in this case, whatever comes next is 25 minus t. So we will write k times 25 minus t. This means that the rate of change is proportional to 25 minus t. This is a separable differential equation. I want all of the p's on the left and I want all of the t's on the right. So really, all I have to do is multiply both sides by dt, and that will get the dt over here. Just like that, I have my p's on the left and my t's on the right. So I can go ahead and integrate both sides of the equation. I'm going to choose to leave my constant out in front of the integral. You can leave it on the inside, it doesn't really matter. But on the left side, the integral of dp is like the integral of 1 dp, and the antiderivative is p. And I'm leaving my k out in the front. I'm integrating term by term. The antiderivative of 25 is 25t. And with the t, I'm going to increase that exponent by 1 and then divide by my new exponent. So I have minus 1/2 t squared. And then I'm going to put my plus c on the end. This is the general solution to the differential equation. Side lesson, just to show you another option, I could have solved this using mental U substitution. So I'm looking at the 25 minus t as my u. I'm not actually going to show the u substitution because if this is u, that means that u prime is going to be negative 1. So all I have to do to compensate for the u substitution is just be sure to put a negative in the front. So I'm going to have the negative k. Now I could take my u and increase the power by 1. So I could turn this into 25 minus t squared. And then I can divide by my new exponent. So I could have a 1/2 in the front. And you know what, maybe I'll put this in front of the k. This would also be a valid solution to the differential equation. Write and solve the differential equation that models the verbal statement. Evaluate the solution at the specified value of the independent variable. Number 19. The rate of change of n is proportional to n. When t equals 0, n equals 250. When t equals 1, n equals 400. What is the value of n when t equals 4? The rate of change of n means dn dt. When something is proportional to n, it means it equals k times n. Side lesson, I want to teach you a major shortcut here. It's about when the rate of change of a quantity is proportional to itself. I'm going to show you how to jump straight to the solution. It's like magic. You're going to love it. But before I teach you what the solution is, I need to show you the pattern so you can recognize it when the rate of change of a quantity is proportional to itself. So this is one example. dy dt is equal to k times y. The rate of change of y is proportional to y. Let's look at a couple more. Maybe p stands for population, and the rate of change of the population is proportional to the population. All right, dp dt is equal to k times p. Quantity is proportional to itself. Let's look at one more. Maybe m stands for mass. The rate of change of the mass is proportional to the mass, right? dm dt equals k times m. So here's the solution. Kabam! Y equals d times e to the kt. D is the constant of integration. I want you to memorize this. What about the other two? You can probably guess. Look at the pattern. That's right. Nothing changes except for its p equals instead of y equals. So anytime the rate of change of a quantity is proportional to itself, you can just automatically skip to the solution, which is going to be, like in this case, m is equal to d times e to the kt. Did you memorize it already? Here we have that same situation. We have the rate of change of n is proportional to n. The rate of change of a quantity is proportional to itself. So the solution for n will automatically be d times e to the kt. So, of course, that is not the end of the problem. We need to figure out what the value of d is and what the value of k is. We need to find these two constants. We will find the values of these constants using the initial conditions that we are given. For example, when t equals 0, n equals 250. Let's plug those two values into the equation to set up one equation. So let's see, when t equals 0, that means that d times e to the k times 0, see t equals 0, then n should be 250. So this whole thing should equal 250. So this red equation comes from these initial conditions. Now let's write another equation using the other set of initial conditions. So plugging 1 in for t, we have d times e to the k times 1, and this should equal 400. So what we have here is a system of equations. We have 2 equations and 2 unknowns. We should be able to use substitution or elimination to solve for d and k. The red equation will be the easiest because of the 0. Obviously, k times 0 is 0. Then we have e to the 0. All right, a constant to the 0 power is 1. So that means we really just have d equals 250. All right, there you go. We already found one of the 2 constants. Yes, kids, it's just that easy. Now we can use this constant in the other equation. So let's plug in 250 for d to help us find k. 250 e to the k equals 400. Dividing both sides by 250, we have e to the k is equal to 400 divided by 250. Dividing the numerator and denominator by 10, we have e to the k is equal to 40 over 25. And dividing the numerator and denominator by 5, we have e to the k is equal to 8 over 5. Remember, we are trying to solve for k, so we need to get rid of this e somehow. We can do that by taking the natural log of both sides of the equation. Natural log and base e are inverse operations, so they cancel each other out. That's going to leave just k on the left side of the equation. So k equals the natural log of 8/5. Ta-da! So now we know the value of d and the value of k. Let's plug them both in and see what we've got. This is a function relating n and t, but we definitely need to simplify this. You know that base e and natural log are inverse operations which cancel each other out. We have to be careful because we don't just have the natural log, we also have this t, so that kind of messes things up a little bit. But if you put in some parentheses right here, this makes sense because when you raise a power to a power, you multiply. So I'm just undoing that. I'm putting this back as a power raised to another power. So this t is the exponent of everything in the parentheses. So now focus on what's inside the parentheses. I have a base e and a natural log. This can cancel out. So I will be left with 8/5. T is the exponent. This is the solution to the differential equation, and we will use it to answer the final question. What is the value of n when t equals 4? So we can just plug in 4 for t, and that'll be the answer. When t equals 4, n equals 250 times 8/5 to the 4th power. And if the problem is calculator active, you can say when t equals 4, n equals 1638.4. Number 20. The rate of change of p is proportional to p. When t equals 0, p equals 5,000. When t equals 1, p equals 4,750. What is the value of p when t equals 5? The rate of change of p is proportional to p means dp dt equals k times p. But the fun part is, this is the shortcut. the rate of change of a quantity is proportional to itself. So we can skip a bunch of work that we could do solving this differential equation and go straight to P equals D times E to the KT. I love this shortcut. Now all we have to do is find the value of D and K using the initial conditions. So using this first set of initial conditions, we will put in 0 for T, and that should equal 5,000. So D times E to the K times 0 should equal 5,000. Similarly, let's put in 1 for T, and that should equal 4,750. So D times E to the K times 1 should equal 4,750. Coming back to this one, K times 0 is 0, E to the 0 is 1, so D is equal to 5,000. Let's put 5,000 in for D in the second equation. So we get 5,000 E to the K is equal to 4,750. Dividing both sides of this equation by 5,000, we get E to the K is equal to 4,750 divided by 5,000. Let's reduce this. E to the K equals 19 over 20. We can solve this for K by taking the natural log of both sides of the equation. Natural log and base E are inverse functions, and they cancel each other out, leaving only K. So K equals the natural log of 19 over 20. So we have the value of K, and we have had the value of D for a minute. So let's take the value of K and the value of D and put them both back into the equation that we got from the shortcut. So here is the equation that we got using the shortcut, and here it is with the value of D and K filled in. Notice that we have E and then natural log of 19 over 20. They're sort of touching each other. I'm dying to cancel these out. However, I have to be careful because of the T. So let's put in some parentheses around the E and the natural log. That makes T the exponent. And again, this is okay because when you raise a power to a power, you multiply. So if I were to take the parentheses away again, it would be the same thing. I would just end up multiplying T times the existing power. So I'm undoing that. Now I can do the inverse operations. The base E and the natural log cancel each other out, and I will be left with 19 over 20. The T will remain as the exponent. So I will end up with the equation P equals 5,000 times 19 over 20 to the T power. So this is the solution to the differential equation. Sometimes this is what they're asking us to find. Sometimes this is the final answer. But sometimes they ask us to find something else. Like now, what is the value of P when T equals 5? But that is trivial. We just need to put in 5 for T. When T equals 5, P equals 5,000 times 19 over 20 to the 5th power. Or, if you have a calculator, when T equals 5, P equals 3,868.905.